Welcome everyone, I'm Jim Corkins and we are on our last part of our voltage module, which is module 3. As always, if you haven't done the reading, please do so. Those readings will be indicated in your Canvas module. Okay, so we are going to be dealing with potential energy problems, and that means we're going to have to review all of energy that you had learned in Physics 111 or Physics 121. I'll advise you to please look up these two videos, and I will link them in this area as two optional videos to watch. That'll help you review for the work that we're about to do. Okay. Now, if you need to recall, I've written out all of the little different equations that go with energy. So first of all, with energy, what we do is we list out the initial energy plus work is equal to the final energy. And then what we have to do is list out all the types of initial energies you could have. Those types are kinetic, which is the energy of motion, which is 1/2 mv squared. The next is potential energy due to gravity, which is mgh. It's the energy of height. And now we have our electric potential energy, which is kind of the energy of voltage, which is Q times voltage, where voltage could be due to a point source, kQ over R, or due to a capacitor or an electric field, which is negative E dot R. Finally, we have the last energy, which is the energy, the potential energy of a spring, which is mu sub s is equal to 1/2 kx squared, where k is going to be the spring constant, how stiff the spring is. And that's basically the energy of a compressed or stretched spring that is compressed or stretched past the equilibrium position. Now you list out those final energies, but a part of the part of the left side of the equation is work, which is work due to a force, like an outside force, like hands or feet or any of that kind of stuff, or due to friction. So these are non-conservative forces. They're conservative meaning they pull energy out of the system or they put energy into the system. All right? So here is basically the setup that we're going to have when we approach energy problems. What I want you to do is list out EI plus work is equal to EF, then list out all the initial energies plus work is equal to the final energies. Have a list of all those the discrete parts of those equations right here. And I also highly recommend creating a little mini force diagram, because that'll help you identify any non-conservative forces, like work that are related to work. Okay? Now, just a real quick review about work. Now, work can be plus or minus, okay? So how you decide if work is positive is if you have a force that is pushing in the direction that you're moving, okay? Okay, so suppose you had this little windsurfer, and they're not moving in the very beginning. And then wind starts to push the little windsurfer, and after a little bit, now they're moving it to the right at 6 meters per second. Okay? So doing this force diagram right here, we would have mg pointing down. We're just going to do a little mini force diagram. And then we have the weight of the surface of the ocean, which is kind of like a normal force. Okay? And that mg is negative. Okay? And we're assuming there's no friction on the surface of the ocean. So if they're getting a force that is pushing them to the right. So that's the force of the wind. Okay? Now that means, since they're not moving in the beginning and then they are moving over a period of not moving, and then they're moving at at a velocity of 0.6 meters per second, that means the acceleration has to be to the right. We are assuming that the velocity and acceleration in the y direction are both 0. Now I'm just saying that this displacement, which is delta x, is 12 meters. So let's go ahead and work with our energy equation. So now this is a picture of the initial conditions, and we're kind of assuming that the wind hasn't touched it yet. The person's just standing up in the water. So what we do is we ask ourselves, these are the list of questions for the initial energy. Are they moving, yes or no? No. Are they a height off the water? No. Is there a voltage working on them? Or are there charges? No. Are there any springs touching them? No. Okay. Now, let's go to the end energy. Are they moving in the end? Yes. Are they a height off the water? No. Are there any voltages? No. Are there any springs touching them that are compressed or stretched? No. So here is our equation. And if you don't know the direction of the work, just leave it positive. Here is our equations right here. Okay? And this also helps you. I basically ask these questions. Is it moving, height off the ground, voltage, spring? And those are those list of energies. Now with work, I said there was no friction in this case. So this is going to be force times the displacement. And that's going to be equal to 1/2 mv final squared. Okay? And we know how far it's gone. We know its displacement. We know its final velocity. We know we're going to assume the mass is, I don't know, 100 kilograms. Sure, why not? 100 kilograms. Actually, let's go with 5 kilograms. This is a toy. All right. So let me just do some real quick mental math. Let's make the mass of the object 2 kilograms. Okay. So let's go ahead and the only thing we could solve for here is the force. So what we're going to do is let's solve for the force. Let's say you're asked to solve for the force. That means we have to divide both sides by that displacement. And this is velocity over delta x. And let's start plugging in our values. Got 1/2 of 2 kilograms times 6 meters per second that we're going to square. And we're going to divide that by 12. So what we're going to find out here, and this is very similar to tutorials. This is similar to layout. You're going to have a force versus distance graph, an energy versus time graph. You're going to have a force diagram, and you're going to have to solve for something. So in this case, let's solve for this. 2 divided by 2, this is 36 divided by 12, so 36 divided by 12 meters, so that's going to be 36 kilogram meters squared per second squared divided by 12 meters. So the force of this object, the force of the wind, is going to be, looks like 3 newtons. So positive 3 newtons, and that works because the force is to the right. Okay, well, in this problem, we're also going to have to, I want you to start using your prior knowledge of force and distance and energy versus time. So let's go ahead and let's do the energy versus time. So let's do the total energy on the total initial energy. So right here, you're supposed to plot the total initial energy and then compare it to the total final energy, right? Well, in this case, the total initial energy is equal to 0. And the total final energy is going to be 36 joules. Now, the problem with this is, if we want to put it on this graph, we know the energy starts at 0, and at some point it's going to end up at being, and I should have left this blank, on yours it'll be blank, but let's just put in numbers here, and this will be 36 joules over some period of time. Well, let's figure out that period of time now. So I forgot to put in little pluses here. So it started off at 0 and it ends at positive 36 joules, right? So we know this, that delta x is going to be equal to V final plus V initial delta t over 2. So we know 2 times delta x divided by V final plus V initial is equal to delta t. So 2 times delta x, that is 24. And we got to remember that this is 0. So that's 24 meters, which is 12 times 2. And the final velocity is 6. So this took place over the period of what looks like 4 seconds. So now we know this took 4 seconds, okay? And now we could use this to calculate power, right? Because power is the change, this is the work divided by delta t. And so we know the change in energy right here is 36. So for example, like this is work. And if work is equal to 1/2 mv squared, and 1/2 mv squared is 36 joules, that means work is 36 joules. So now this is going to be 36 joules divided by 4 seconds. So the amount of power that is happening here is 36 divided by 4, which is 9. That is 9 watts. So this is going to be 9 watts. Okay? So that's the reason why these graphs are powerful, because you could do a lot with them. You just have to think of a few things. So this is 9. Whoops, I'm sorry. This was 4 seconds. So we have the power here. Now let's go ahead and graph that force. Well, the force that it's experiencing across the 12 meters is what we determined is positive 3 newtons. So this is positive 3 newtons, and I'm just going to put it right up here. And it did that for a period of 12 meters. And the great thing about graphing this too is, you know, the slope of this is not meaningful. Whatever newtons per meter here is, I don't know what that is in regards to an actual force. A newton meter could be like a spring constant, but in this here, we're not graphing a spring constant. In this context, though, the area under here is meaningful. And so this area we could use to confirm some of our numbers right here. So the area of this below this is actually the amount of energy, right? So here's what I mean. So this is the amount of work. So work here, this area, is a force times a displacement, right? And it's a dot product. Well, in this case, it's a constant positive 3 newtons times 12 meters. So that's going to be equal to positive 36 joules. Okay? So these tutorials that you're going to do are linking a lot of your old knowledge, and hopefully your conceptual understanding is going to start becoming more integrated. We tend to teach these topics separately from each other. But really, when I think of these concepts, and my colleagues do as well, they are all interweaved with each other. And doing these tutorials that we're about to do is going to teach you to integrate that knowledge, okay? And furthermore, what this is also teaching you is that when work is positive, an object is speeding up. That's what it means. That's what positive work means. And positive work will end up being positive power, right? You're adding energy to the system. It wasn't moving, and then you gave it a shove, and then it was moving. So, and that shove was the force across of whatever displacement that the force was working on the object. The antithesis over here is when work is negative. So same situation, we're going to say the mass here again is going to be, what did we call it? 2 kilograms. So it's like a toy object, like a little toy surfer. We did call it 2 kilograms. Okay, so we're going to do this again. But in this case, the person's moving to the right and the wind is pushing them to the left. And then they eventually come to a stop. Okay, and so we'll see what I mean by this. So let's ask our questions here. Let's get started. So are they moving in the beginning? Yes, they're moving to the right at positive 6 meters per second. Their height is 0 off the water. There is no electric forces, no springs. In the end, they come to a stop. Their height is 0. There's no electric forces and there's no springs. So what we have is Ki plus work is equal to 0. So what this means is the final energy here is 0. Where in the other one, the initial energy was 0 because it was not moving. All these were checked off. So here when we put in our 1/2 mv squared, plus work, that's going to be equal to 0. So when we bring this onto the other side, what you could see is now work is negative. And this is going to work out because we're using the same numbers. And I'm just going to skip to the case. This is going to end up being 36 joules. And that force times that displacement is going to be equal to, negative 36 joules. It's going to be negative 36 joules divided by that displacement. So that force is going to be negative 36 joules divided by 12 meters, which is to the right 12 meters. So that's going to end up being negative 3 newtons of force. So when we do our force diagram here again, that's negative mg. We have the same surface of the ocean, so that's not changing. So the normal force is still positive. But in this case, the force working on this object, where in the other one it was to the right, this force is to the left. Oops. Is negative. And that means the object will be slowing down. It'll have a negative acceleration. Okay. The velocities are 0 in the y direction. So that's what we're saying. So this force, which we predicted is going to be negative, is going to be a negative 3 newtons of force. Okay. And so since we have negative 36 joules, okay, the work is negative 36 joules. And where we could see that the initial kinetic energy is positive 36 joules, but the final energy is 0. So again, I'm going to put positive 36 up here, joules. The initial energy is that. The final energy is 0. So you could see this is going to be a negative slope. And then, just like before, we could use this. And I'm just going to go right to the equation. Actually, I'll write it out again. 1/2 V final plus V initial times delta T. Right? And then, through the magic of algebra, that's our delta T. And we end up getting similar things, except this is going to be this will be positive 24 meters, because 2 times positive 12, right? This is positive 12 right here. And the final energy is 0. The initial energy is positive 6 meters per second. And so the time on this is 3 seconds, right? Just like before. So this is 3 seconds. So it's basically the same time frame and the same distance. But in this case, the force is going to be a negative 3 newtons that is working on it for the total through the total displacement, which is positive 12 meters. So this part right here is there. And so this area, this is going to be our area, which is going to be the work, which is negative 3 newtons times 12 meters. So that's negative 36 joules of work. And that works out. F delta x is negative 36. And the power here is a negative slope, which is going to be equal to work divided by time, and that is negative 36 joules divided by 3 seconds, and that's going to work out to be negative, oh, I'm sorry, that should be 4 seconds. How did I get 3 there? 24 divided by 6 is not 3, Jim. That is 4 seconds. 4 seconds. And 4 seconds. So this is negative 9 watts. So by doing these tutorials, you're going to get a good review of basically Physics 111 and integrating in Physics 112. Okay? Now, one last thing to talk about. So again, if an object is speeding up, just to review these 2 slides, if an object is speeding up, that's positive work. You're adding energy into the system. The object wasn't moving. You had to add energy into it to make it to start to move. So you had to speed it up. If the energy was moving and you pushed it opposite the direction it was moving, so somebody pushed a chair at you and it's coming towards you, you have to push opposite the direction it's moving to slow it to a stop. So you're taking energy out of the system. So that's why you end with a negative power. Okay. The other thing we have to pay attention to is, just like the electric field stuff, only the part of the force that is parallel to the displacement contributes to work. Okay, so for example, if you pushed up into the, if a force was pushing up into the right while an object was moving to the right, this part of the force that is straight upwards, the F sine of theta, does not contribute to the work at all, right? You would neither be speeding the object up or slowing it down, okay? If it's moving to the right, only the parallel portion of the force, the force that is the part of the force that is parallel to the displacement, is contributing to the work in speeding it up or slowing it down. All right. Now that we've talked about that, let's do at some of your tutorial examples. Okay? So, in these tutorials, in these recordings, what we're supposed to do, and these are the same instructions that are in the student tutorials, you're supposed to find the solution for whatever you're supposed to be asked to solve for. In this case, the first one is about deciding if there is energy lost. So if work is present. You're supposed to complete a force diagram. So I'll scooch out so you could see this. Supposed to complete a force diagram. Then we're supposed to complete the electric force versus displacement graph right here, and then find the area underneath that to calculate the work done by the electric field. And that'll help us find this. So we'll have to plot the initial electric potential energies, the final electric potential energies. We'll have to find time, the time it takes for it to do whatever type of motion. And then from there, we'll be able to calculate power. So we're going to do all of these, right? And these instructions will be in the front of your quiz and your quiz. All right, let's move on to the first one. So you have a problem that's similar to this, but a little bit easier. I think it deals with a constant electric field. Mine is a little bit more difficult as it has an electric field that is not constant. So this may seem a little bit weird, but I had to edit this down a little bit. So if there's something missing from here, on my first one, I took out the force versus time because it was just adding, force versus displacement is adding too much time to the entire video. So I apologize. I did take it out from your first page as well. But let's go ahead and get started though. So in this problem, in my case, the total energy is not conserved. I forget whether or not it's the case with you, but with me, I'm saying the total energy is not conserved. Likely, there's probably some kind of friction or something going on. Let's start off with a force diagram. So we know it's going to be, it's got mass times gravity down. We have our normal force is pointed up. And it looks, since they're repelling each other, that the electric force caused by that positive 1 nanocoulomb charge is working to the right. So this object, it says it's positive 4 coulombs. It weighs 0.33 kilograms, and it's initially at rest here. And then later on, it's moving to the right. And we're not sure whether or not the energy is conserved, meaning there might be an outside force. And likely, if that's true, the outside force will be pointed to the left, right? Because it didn't say whether or not there was any energy added to the system, which would be another force to the right. So I'm just guessing here. So this is a question mark. If it's negative, if this work ends up being negative, then this is true. If it ends up being positive, then this green arrow should be pointed to the right. Either way, it is speeding up as it's moving to the right, and it has no velocity in the y direction or acceleration. Now let's do our energies. It is not moving in the beginning. Its height is 0. No, it's got a voltage on it. Its spring is 0, and there's a work. It does have a final velocity. Its height is still 0, and there's no springs touching it. Okay? So this is our energy system. So U sub Q I equals K final plus U sub Q F. Okay, that is our mix of energies. Whoops, I forgot the work. U sub Q I plus work. And if you don't know the sign of work, just leave it positive. The math should work itself out. Now, the charge on the cart, I'm just going to call Q for right now. Now there's a voltage acting on it, right? Q times V. And that's the initial case, plus work. That's equal to 1/2 mv final squared. And we know that final velocity is 6 meters per second at the 2 meter mark, which is going to be the charge on the cart times the final voltage acting on it. Now I need to go one more level down because I have to define that voltage. It's caused by a point charge, K, and I'll number this now, KQ2, which is this positive 1 nanocoulomb charge at the initial position, plus work equals 1/2 mv final squared plus Q1 times K times Q2 all over the final position. Now we're going to start tossing in numbers here. Okay, Q1 is positive 4 coulombs. K is 9 times 10 to the 9th Newton meter squared per coulomb squared. Times our positive 1 times 10 to the 9th charge, and that's 10 to the negative 9th charge, all over the distance 1 meter. Plus work equals 1/2 the mass, which was 0.33 kilograms, times the velocity, which is 6 meters per second that we're going to square, plus all of this here, but divided by 2 meters. Now in here, when we're doing our math, we just have to remember that 10 to the positive 9 times 10 to the negative 9 is 1. So this right here is going to be 4 times 9 divided by 1. So what is that? 36 joules plus work. That's going to be equal to 6 squared, which is 36, divided by 1/2, and this is 1/3, so that'll be 1/6. So 6 squared divided by 6, that is going to be 6 joules, plus right here, this is going to be 4 times 9 divided by 2, so that's 18 joules. Incidentally, this is our initial potential energy due to the charge, and this is our final potential energy due to the charge that we're going to have to map up on that energy versus time graph. So what we're going to have here is 36 joules plus work equals 24 joules. Now when we subtract that 36 onto the other side, it looks like we are going to get a loss of energy of 12 joules. And that is our work. So I would ask you to type that in. You'd have to type in negative 12. You're supposed to round your final answers to the whole number. Okay. Now, we know the initial electric potential energy is 36. The final is 18. So I'm going to just put those numbers here, up here. I'll put positive 36 joules right there, positive 18 joules right there. And so it's going to be dropping off to that negative 18 joules right there. But we need a period of time. How do we get that time? Well, we have to think back to our motion equations. So our motion equation is going to be delta x. The only one I could think of using right now is delta x equals 1/2 v final plus v initial times delta t. And then so doing the algebra through the magic of algebra, equals delta t. We get this. So the distance it moves is a total distance of 1 meter. So that's going to be 2 times 1 meter displacement over the final speed was 6 meters per second. The initial was 0 meters per second. So this is going to be 2 divided by 6, which is 0.33 seconds. So this is over 0.33 seconds. Now to calculate the power, so let's calculate the power here. So this is power is the slope of this line, okay, which is a loss of our 24, loss of our, it looks like it's a loss of 18 joules right here. This work, I just want to be careful here. This is a loss of the total amount of energy from the system. So this is the total amount of energy. However, the loss or change in the electric field, because the electric field is getting weaker the further it goes from a point charge. We're just plotting the loss of power due to the point charge working on our cart, which is 18. So it drops. Okay, so this is the delta U right here, sub Q, over time, which is the final potential energy, which is 18 joules, minus the initial potential energy, which was 36 joules, divided by 0.33 seconds. So that power is going to be negative 18 times 3. So negative 18 times 3, what is that going to work out to be? 18 divided by, nope, 18 times 3. 54. That's a loss of 54 watts. That's how much the electric field, electric energy was dropping off by. So in our, what I'll ask you to do is I'll ask you, what's this answer, and then power. So I think I'm asking for the value of power on all of your pages, on all your work. But you'll have to solve for whatever I'm asking you to solve for. And I think this is the only one where you're not plotting the force, the electric force versus displacement, just to conserve time. Okay, let's go ahead and get started on your next one. Let's do the next one here. Zoom in a little bit more. Okay, so we have a cart that is a mass of 4 kilograms. So it's 8 kilograms, 4 kilograms of positive 8 coulomb charged cart that can move without friction. It's at a position 1 meter, not moving. Later on, the cart has sped up to 2 meters per second at a position of 2 meters. And they're saying total energy is conserved. We're supposed to calculate the electric field. Okay, well, let's do a force diagram. Since we know energy is conserved, we could probably accurately create this little force diagram. So mg is down, the normal force is up. And the only thing acting on the cart's motion horizontally in the direction of its motion is the force due to the electric field. The object is moving to the right, it's accelerating to the right, it's not moving up or accelerating up or down. Okay, so real mini force diagram just to kind of make sure we completely understand the prompt. Now, in the beginning, it's not moving. Its height is 0. It does have a voltage working on it. There are no springs touching it. In the end, it is moving. Its height is still 0. There's no springs touching it, and it's got a voltage acting on it in the end. We do also know there is no work present. So what we have is U sub qi equals k final plus U sub qf. And we're going to have to plot these initial and final energies of the electric field right up here. So let's go ahead and figure those out. The problem is we need to figure out what the electric field is first. So we have a positive 8 Coulomb charge, and it's being acted upon by an electric field that we don't know that value, but its position is 1 meter at that point. We do know it is moving, so I'm going right to the numbers. This is 1/2, and the mass is 4 kilograms, and it's moving at 2 meters per second, and we're going to end up having to square that. And that's going to be plus 8 coulombs times negative E times 2 meters. Okay, and that's the final energy. All right, let's multiply some stuff out here. So this is going to be negative 8 Coulomb meters times electric field. And this is going to be 4 times 4, 16. 16 divided by 2 is going to be 8 joules. This will be negative 16 Coulomb meters times electric field. All right, let's add the electric field on the final energy onto the other side. So the final energy is going to be now positive 16. We brought it to the other side. Coulomb meters times electric field minus 8 Coulomb meters times the electric field, and that's going to be equal to 8 joules. So when we subtract these two, we're going to get 8 Coulomb meters times the electric field equals 8 joules. And so the electric field is going to be, I might need that room, so we could say that the electric field is going to be equal to 8 joules divided by 8 Coulomb meters. And remember, a joule is a Newton times a meter, right? So those meters are going to cancel out. And what we're going to get is positive 1, so it's going to be a rightward pointed electric field, newtons per coulomb. So that is what we are asked to solve for. Okay, positive 1 newtons per coulomb. Okay, now that we know that, the potential energy of this in the beginning is going to be this part right here. This is the initial potential energy. This, again, is the final potential energy. So initial potential energy is going to be 8 coulombs times negative 1 newtons per coulomb. It's a negative in the front, so negative times a positive. There you go. times 1 meter. So this is the initial energy is going to be -8 joules. Okay. And the final potential energy, which is +8 coulombs times a -1 Newton per coulomb times 2 meters. So this is going to be -16 joules. Okay. All right. Now, let's go ahead and figure out the power here. And then we'll roll back to figuring out the electric force, which is very easy to do. So we know U sub Qi, and I'll do this over here. U sub Qi was -18 joules. And we know U sub Qf is going to be, I already lost it, -16 joules. And that should have been -8 joules. So -8 joules and -16 joules. And when we go to plot this, we need to figure out the velocity again, right? So again, delta x 1/2 v final plus v initial delta t. It works in this case as well. So 2 delta x over v final plus v initial. So 2 times a +1 meter displacement, right? It went from 1 meter to 2 meters over 2 meters per second. So this time is going to work out to be 1 second. So its velocity, or its energy, is changing from, let's put -8 joules here, -16 joules here. So the electric field's loss of energy is over the period of 1 second. So it starts here and ends right here. Okay? So we're saying that's, I said it was a loss of energy. It's actually a positive energy. So this is speeding something up. It's adding energy to the system. Okay? So the power here, which is going to be work divided by delta T, right? Well, that energy, that's going to be, it's going up by 1. So that's going to be +8 joules over 1 second. So that's going to be a +8 watts. And that's the other thing we are asked to solve for, right? Let's plot the force now. Okay. Again, force is going to be equal to the potential energy, and we got to be careful here over distance, right? So over initial position, right? We have to be careful because that force, we're going to have to put absolute value because the force was to the right. So even though this is a -8 joules of energy at 1 meter, it was being pushed to the right. So this is going to be a force of +8 newtons. And if you go over here, this force is going to be the same thing. We're going to be doing the same thing, which is going to be U sub Qf over the final position, which is going to be -16 joules over the 2 meter position. This is going to also work out to be +8 newtons. Okay? Because it's in an constant electric field, the force is also constant, if you remember that from our first module. So positive 8 newtons. It started out at 1 meter. It ended here at 2 meters, right? So this is going to be a constant force across that displacement, okay? So the amount of work done here is going to be equal to 8 newtons times 1 meter. So that's going to be a positive 8 joules. Okay. I'll zoom in to this. So this is the second problem in the tutorial explanation. The final part to this is this. So at one point, I'm going to give you an electric field versus displacement, or versus distance, okay? An electric force versus distance. And I'm gonna describe some things. So in here we have an electric force that is applied to a 12 kilogram object having a negative 2 coulomb charge within a changing electric field. And if this was a constant electric field, it would be horizontal, just like the last problem. Okay, as shown here. Okay, now the total energy is conserved. Okay, this is just the electric field energy. Okay, so it was started at rest, and then it's going to be speeding up. Okay, so we don't know what's going to happen. So it's going to be speeding up across a distance of 6 meters. Okay, now there's a lot of ways we could do this problem. Okay. But the best way is I'm gonna start with the energy. Well, actually, I'm going to start with the force diagram. So this is mg, which is the same force diagram that we've been doing, except for the first one. And then we have the electric field, which is pushing it to the right, right? We have whatever that is, pushing it to the right. And I don't know what that is, so I'm just going to call it an E field right now. It's definitely due to a charge of some kind, right? Because that electric field is dropping off to 0. That force is positive the whole time. So it starts off with a negative force, and then it's getting pushed to the right with a positive force between 5 and 6. So I don't know, there's something flip-flopping here. So this electric field seems to be flip-flopping in some case. But we do have a negative charge here. So I'm going to put question marks here because I don't know. We just want to know what the final velocity is after it's doing whatever crazy motion it's doing. So it starts off in this problem not moving. Its height is 0. It's got a voltage on it because it has an electric force acting on it, and no springs are touching it. Also, no outside work. It is moving in the end, and we have this. So we have basically the same kind of chunk of energy that we did last time. U sub QF. Okay. Now, what are we going to do here? I'm going to bring this U sub QF onto the other side. So this negative U sub QF plus U sub QI is equal to the final kinetic energy. Now I'm going to do something off to the side so you can see how I'm about to reason through this. Okay, so first of all, we'll have to calculate those two numbers, but let's go ahead and do something right here. This U sub QF here, if delta U is U sub Q F minus U sub Q I. But if I take the negative delta U, what we do is multiply this by a negative number. And when we do that, negative delta U, that's going to be equal to negative U sub Q F, and negative times negative is a positive U sub Q I. All right, so you can see that this is actually negative delta U. Okay, final. Right there. So what we know from here is that the area relative to this, this is delta U, incidentally. This total area, which is going to be the area underneath this line, right here, this area plus this area right here, that is U sub Q. Okay, so here we go. Let's figure out those areas. This red area right here is going to be, it's the work due to the electric field. So this is going to be, this red area is 10 times 5 divided by 2. So negative 10 newtons times 5 meters. And since it's a triangle, we're going to divide it by 2. So that's going to be negative 25 joules. This purple area right here is going to be positive 2 times 1. So positive 2 newtons times 1 meter divided by 2. So that is going to work out to be, what is that? That's just plus 1 joule. So the total delta U here, which is the work done, by the way, total delta U here, that is going to be negative 25 joules plus 1 joule. So that is going to be 24 joules. So now we figured out what delta U is. So this is negative 24 joules. And this is going to be 1/2 the mass, which is 12 kilograms, times the velocity, final velocity that we're being asked to solve for. Oh, you know what? I forgot to mention something. The total work done by this. So, work done by the electric field is the negative of this, right? Because the negative of the electric field. So, this area. Oh, sorry. Yeah, you'll see in a second. We'll calculate this, and I just made a kind of making it overly complicated. But when we calculated this, whoops, hold on a second, I'm going to, okay. I don't know what's going on here. Okay, so when we put this number in right here, by the way, this should have been a negative number right here. So this is going to be a negative of a negative 24 joules, right? Negative 25 plus 1, negative 24 joules. So this is going to be 24 joules, and that's going to be equal to 6 kilograms, V final squared. So 24 joules divided by 6 kilograms, that's going to be V final squared, which is equal to 24 meters squared per second squared, right? So V final, we square root both of those. We're going to get V final, which is going to be 2 meters per second. Okay? So that is our first calculation. Okay, well, let's move on and let's go ahead and plot the energy versus time. The problem here is we know the change in potential energy due to the charge, which I should put a little Q here, but we don't know the starting energy, so we have to pick one. Okay, so I'm going to just pick its starting energy as positive 24 joules. Sure, why not? And then it's going to be dropping off to 0 joules. And we need to figure that amount of time here. Okay, so again, 2 delta x over V final plus V initial, that's going to be equal to delta t. And we've done how that comes about before. So this is going to be 2 times 6 meters over 2 meters per second plus 0. So that is going to be 6, 12, 12 divided by 2, 6. So 6 seconds. So that's going to happen in a period of 6 seconds, right? And so the work, the power, which is this drop-off, is going to be your change in potential energy due to the field over time. That's going to be negative 24 joules over 6 seconds, which is going to be negative 4 watts. And that's the other thing that we have to solve for. All right. Well, this is your last tutorial in this module. I hope this helps you. Have a great day.